Today, we're going to be talking about rational functions and infinite series, and I'm going to be showing you a clever way to see all rational functions as an infinite series. This method comes straight from Chapter 4 of Introduction to Analysis of the Infinite, a textbook written by Leonhard Euler, one of the greatest mathematicians in history. But you're probably wondering how rational functions have anything to do with infinite series. That we will see shortly. Here before us, we have an example of an infinite series: 1 plus 1 half plus 1 fourth plus 1 eighth plus 1 16th plus 1 32nd, and so on. You've probably noticed these are the reciprocals of the powers of 2. 4 is 2 squared, 8 is 2 cubed, 16 is 2 to the fourth, and so on. And this is a geometric series. Each term is half the previous term. At first glance, many of you may think that the sum is infinite, as we're adding an infinite amount of terms. How could it not be infinity? However, this is not the case. The sum is actually finite. To see this, we have to manipulate the sum in a clever way. Let's set it equal to s. So s equals 1 plus 1 half plus 1 fourth, etc. What happens if we take half of s? We see that half of s is 1 half plus 1 fourth plus 1 eighth plus 1 16th plus 1 32nd, etc. Wait, this looks familiar. This will actually help us a lot. We just need to take one clever leap. And that leap is to subtract s and 1 half of s. Then all of these terms, 1 half, 1 fourth, 1 eighth, all of them except 1 cancel out. Then we have s minus 1 half of s equals 1, which means that 1 half of s is 1, so s is 2. It doesn't actually matter what number we're taking the powers of. As long as its absolute value is less than 1, the series will not diverge and not go to infinity. So 1 half, 1 third, 1 fourth, all of these numbers will give you a sum that does not go to infinity. So we have here s equals 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth, and so on, where x is less than 1. Then we multiply s by x to get xs equals x plus x squared plus x cubed, and so on. We subtract and factor to get s times 1 minus x equals 1, which means now that s equals 1 over 1 minus x. This is a rational function. So now we see how that infinite series is exactly equal to a rational function, and this is a topic we can further investigate. So, in his Introduction to Analysis, Euler tells us to look at a proper rational expression, meaning the degree of the denominator is greater than the degree of the numerator. So first, he shows us the most simple example with a degree 1 denominator. We have the expression a over alpha plus beta z. So how can we see this as an infinite series? Euler says, let's just pretend it is, and he sets it equal to a plus bz plus cz squared plus dz cubed plus ez to the fourth plus fz to the fifth, and so on. But how does this help us? Are we any better off? We don't know a, b, c, d, or anything. We just have a bunch of unknown coefficients, infinitely many of them. But Euler sees through this. He cleverly cross-multiplies to get little a equals alpha plus beta z times big A plus bz plus cz squared, etc. Now he multiplies it out to get alpha big A plus alpha bz plus alpha cz squared, and so on, plus beta az plus beta bz squared plus beta cz cubed, and so on. Still, there's something else we need to notice. Euler realizes that little a is the same thing as little a plus 0z plus 0z squared plus 0z cubed, and so on. Then he groups the terms of the series to get coefficients for the powers of z and matches both sides of the equation. So little a corresponds to alpha big A, so little a equals alpha big A, and therefore big A equals little a divided by alpha. Then 0 equals alpha b plus beta A. So b equals negative beta times big A over alpha, which equals negative beta little a over alpha squared. And the same goes for c. So c equals beta squared little a over alpha cubed. We start to see a pattern. Given any arbitrary coefficient r, we know that alpha r plus beta q, the coefficient before it, equals 0, which means that r equals negative beta over alpha times q. This tells us that each coefficient is the one before it multiplied by negative beta over alpha. In other words, the coefficients are a geometric sequence. So now we have a over alpha minus beta z equals a over alpha minus beta a over alpha squared times z plus beta squared a over alpha cubed times z squared minus beta cubed a over alpha to the fourth times z cubed, and so on. So if we know little a, alpha, and beta, we can write any first-degree proper rational function as an infinite series, as long as alpha is not 0, because then we would be dividing by 0, which we can't do. So let's see an example. We'll set little a to be 2, alpha to be 3, and beta to be negative 5. So we would have 2 over 3 minus 5z. To write this as an infinite series, we substitute our values in, and we see it's equal to 2/3, then plus negative of negative 5/3 times 2/3 times z, which equals plus 10/9 of z, then minus 50/27 of z squared, plus 250 over 81 times z cubed, and so on, forever. And that's how we see first-degree rational functions as infinite series. In part 2, we'll go over how to see second-degree rational functions as an infinite series, and then we'll see any degree rational expression. See you then.